In our previous unit, we talked about how liquids and solids are held together by intermolecular forces. Remember that those IMFs are always some sort of electrostatic forces that cause the individual atoms or molecules in a material to be attracted to each other. Liquids and solids are sometimes called condensed states of matter because the intermolecular forces dominate and keep the molecules packed pretty tightly together. If those forces are strong, the material tends to melt and boil at higher temperatures because it takes more thermal energy to overcome the attractions. But what happens when you add enough thermal energy so that the movement of the molecules overcomes the intermolecular forces altogether? When this happens, you end up in the third phase of matter, the gas phase. We have a whole section of this unit devoted to how gases work because they kind of play by their own unique rules. In the condensed phases, the solids and the liquids, you can add a little heat or squeeze the material a little, for example, and nothing much really happens, at least until you hit a phase change. And again, that's because the intermolecular forces in the material are determining how that material behaves. For gases, though, the intermolecular forces don't really matter anymore. It's just a bunch of particles flying around and taking up as much space as they can. And because of this, the behavior of a gas basically comes down to A, how many particles we have, we'll call that the number of moles, B, how fast the particles are flying, we'll call that the temperature, and C, how much space do they have to fly around in, we'll call that the volume. There are a couple of other things that are wrapped up in this, but the first thing we'll want to do here is understand how those qualities are related to each other. So, let's begin by picturing a balloon, for starters. Most of us can visualize what would happen if you started with some air inside a balloon and you just added more air to it. We'd expect the balloon to expand, right? This is kind of the simplest thing ever, but we might as well write it down, because what we've done here is relate two of those qualities that we mentioned before, the number of moles of a gas and the volume. To be precise, since increasing one causes a corresponding increase in the other, we would say that the number of moles of a gas is directly proportional to its volume. Believe it or not, this little formula is important enough to be considered one of the 4 special formulas called the gas laws, and it even has the distinction of being named after a dead scientist, though you really don't need to worry too much about the names. We can actually knock out some more of the 4 gas laws without introducing anything new at this point. Take that balloon again, and this time think about what would happen if we took the air inside it and heated it up. Maybe a little harder to picture than the first example, but let's think about what would be happening inside the balloon. Remember that we said earlier that temperature is really a measure of how fast the gas particles are moving. Let's just take that for granted for now. If you increase the temperature then, the particles will start moving faster, which will cause them to collide much more often and with more force against the rubber walls of the balloon, and that will push the walls of the balloon further apart. In other words, the gas inside the balloon will expand as we raise the temperature. And if we're going to write that down in math terms, we'd say that the temperature of a gas is directly proportional to its volume. That's another gas law for you. And incidentally, this is the reason why hot air balloons work. The air inside the hot air balloon is just regular air, but if you heat it up, it expands and becomes less dense than the air outside. And things that are less dense than their surroundings will float. So if your balloon is big enough, you'll have a pretty ingenious way of getting off the ground. We've covered 2 gas laws so far, and before moving on to the other 2 gas laws, we need to introduce one additional concept that's really important for gases, and that's the idea of pressure. In its most basic sense, pressure is just a force that's acting over a certain area. And gases are really good at doing this because, as we've seen, they expand to fill the space they're in, and gas particles are constantly colliding with the surfaces of their surroundings. Anytime there's a collision, a tiny bit of force is exerted on that surface. So if you're dealing with a gas, you can always measure its pressure along with the other qualities we've identified so far, and you can probably guess that pressure is going to be tied up in relationships with those other qualities. Before we get there, it's important to pause for a second and recognize that there are just a ton of different units for measuring pressure. This tends to happen when it's a quantity that's been studied for centuries, but unlike a lot of the other properties in science that we've studied so far, where there's a standard unit that's almost always used, like the metric system for lengths, volumes, and masses, for instance, you're going to see a broad mixture of pressure units in modern literature. The true standard SI unit for pressure is the Pascal, but we honestly don't see that one used all that much these days. Instead, you're generally more likely to see pressure measured in either atmospheres or torr. The first unit is roughly defined by the pressure exerted by the gas in Earth's atmosphere, where 1 atmosphere is equal to the average atmospheric pressure at sea level. The second unit there is a callback to the way old barometers used to work. You can get a somewhat reliable weather forecast by measuring changes in Earth's atmosphere, and in the olden days you would do that by using a stick barometer. Stick barometers had a wide reservoir of some liquid open to the atmosphere, connected to a narrow tube like that of a thermometer. Pressure from the atmosphere pressing down on the surface of the reservoir would cause the liquid to move up into the tube where you could read a precise measurement. Low pressure usually means high winds and stormy weather, while high pressure usually means milder conditions. The units for this measurement are named after the scientist who invented the device, but they're also nearly equivalent to the millimeters of height that you'd read off of a standard stick barometer back in the day. People most often used mercury in the first barometers because it wouldn't evaporate over time, like most other liquids. So you'll see millimeters of mercury as a common unit of pressure. Oddly, this is still the one favored in certain medical settings, so you may see it there also. There's also a unit called bar, which is equal to 100 kilopascals and was sort of designed to be a more useful standard measurement based on the SI unit, but anyway, the point is that there are a lot of units of pressure, and you may have to use your old dimensional analysis skills to convert between them in this unit. Okay, so back to the final 2 gas laws. Going back to our balloon, let's imagine what would happen to the pressure inside the balloon if we squeezed it down to a smaller size. Basically, we'd be decreasing the volume, but keeping everything else the same. What would happen to the pressure? Well, the gas particles are still moving just as fast because we didn't change the temperature, but they're going to be hitting the sides of the balloon much more often now that they have less space to fly around in. This is going to increase the pressure. So as volume goes down, pressure goes up. This is called an inverse relationship, and we would write that the pressure of a gas is inversely proportional to volume. Okay, one more left, and this one shouldn't be much of a surprise either. Say you wanted to see how pressure and temperature are related now. We can't really use our balloon anymore because we need to hold the volume constant in this scenario, so instead let's picture a metal gas cylinder like the ones we use to feed the air taps in the chemistry lab. Remember that if you increase the temperature, you're increasing the speed of the gas particles. What would happen to the pressure in this case? Well, you haven't changed the shape of the cylinder, but you're going to increase the collision frequency of the gas particles with the walls of the cylinder because they're moving faster now. More collisions equals more pressure. So our last gas law is another direct relationship. The pressure of a gas is directly proportional to its temperature. And there you have it. Those are the 4 gas laws that describe how the individual qualities of a gas are related. It's worth noting at this point that we can't really do anything with these statements yet the way they're written, because that proportional sign isn't an equals sign, so we can't do algebra with these things. But in the next video, we're going to see how the gas laws can combine together to help us predict and calculate those properties. See you there.